the 1800s blueprints that modern engineers can't reproduce, and no one can explain why. There is a fascinating and well-documented phenomenon in engineering and the history of technology. Multiple 19th century construction and manufacturing techniques cannot be easily replicated using only original blueprints and specifications, even with advanced modern technology. This is not a supernatural mystery, but a demonstration of something that historians of technology call tacit knowledge, a concept developed by philosopher Michael Polanyi in his work The Tacit Dimension, published in 1966. Polanyi argued that we know more than we can say. Much technical knowledge resides in bodily skills and intuitive judgments that are difficult to codify into words or drawings. When the last generation of craftsmen who mastered technique retires without fully transmitting knowledge through hands-on learning, technique can be partially lost even with seemingly complete documentation. This phenomenon has been extensively studied by historians such as Eugene Ferguson in his book Engineering and the Mind's Eye, MIT Press, 1992, which documents how visual and tactile knowledge was central to engineering before the computer age. Let's examine specific, well-documented examples of 1800s techniques that have proven challenging to replicate, based on published academic research and analysis by historians of technology. Importantly, we are not saying that replicating these techniques is impossible, but that precise replication is not as simple as following original plans, revealing gaps between explicit documented knowledge and tacit knowledge embedded in practice. The first widely studied example comes from stone arch bridges. According to David Billington, professor emeritus of civil engineering at Princeton and author of The Tower and the Bridge, Princeton University Press, 1985, masonry arch bridges built in the 18th and 19th centuries demonstrate structural sophistication that modern engineers often underestimate. Plans show arch geometry and stone dimensions, but techniques for selecting, cutting, and positioning stone were transmitted through master-to-apprentice learning. A documented case study is Pontypridd Bridge in Wales, built in 1756 with a span of 43 meters, which was the world's largest single stone arch for decades. When modern engineers analyze the structure, they are impressed by the material optimization and stability achieved not through formal mathematical calculations, but through empirical knowledge and physical models. Manual precision tolerances, scraping, and Victorian manufacturing. One of the best documented techniques illustrating tacit knowledge is scraping, the manual scraping of metal surfaces to create precision flatness. This technique is described in historical workshop books such as Machine Tool Practice by R.R. Moore, McGraw-Hill, multiple editions since the 1930s, and continues to be taught in some toolmaker training school. The process involves using a cutting tool called a scraper to remove microscopic amounts of metal, guided by the application of engineer's blue dye, Prussian blue, on a precision reference plate. When the surface being worked is rubbed against the plate, raised areas capture the dye. The craftsman scrapes these areas, checks again, and repeats the process hundreds of times. The final result can have flatness of a few microns through a completely manual process. According to Wayne Moore, author of Foundations of Mechanical Accuracy, Moore Special Tool Company, 1970, which documents the history of precision machine tools, components of Victorian steam engines often showed tolerances that rival modern manufacturing. A specific example comes from Corliss engines, patented by George Corliss in 1849. Analysis of engines preserved in museums such as the Smithsonian Institution shows that cylinders and pistons had clearances of a few hundredths of a millimeter, achieved through manual scraping. This technique seems simple when described, but requires years of practice to develop, as noted by machinist and educator Tom Lipton in his work on traditional workshop techniques. A craftsman must develop an extremely refined tactile sense to detect height irregularities of a few microns using a tool in hand. He must learn the exact angle, pressure, and pattern of strokes. In Philip Duclos's book, Shop Wisdom, Village Press, 2003, which compiles knowledge from experienced machinists, multiple contributors note that it takes approximately 5 years of regular practice to develop real proficiency in scraping. Paradoxically, modern CNC machines can produce mathematically flatter surfaces, but these ultra-smooth surfaces sometimes have inferior performance properties for specific applications. A manually scraped surface has a microscopic texture that retains a lubricant film better, a concept explained in tribology texts, such as Principles of Lubrication, edited by A. Cameron, Longmans, 1966. Victorian craftsmen understood this intuitively through practical experience. If you're fascinated by how technical knowledge from centuries past still defies modern understanding, leave a like now. Subscribe to the channel and activate the bell for more explorations based on real historical research. And if you want to support this work of documenting authentic technical knowledge, click the Hypar button below. All information in this video is based on verifiable sources that you can consult. Now let's examine historical materials that are impossible to replicate. Historical materials: Roman concrete and traditional mortars. Although the focus is on the 1800s, it is impossible to discuss historical materials without mentioning Roman concrete, which has been the subject of extensive scientific research. A study published in American Mineralogist in 2017 by Marie Jackson and colleagues at the University of Utah, Jackson et al., Phillipsite and Al-tobermorite mineral cements produced through low-temperature water-rock reactions in Roman marine concrete, Volume 102, demonstrated that Roman concrete used in ancient port structures continues to gain strength through chemical reaction with seawater that produces rare Al-tobermorite crystals. Modern Portland cement does not have this self-healing property. For the 1800s period, lime mortars exhibit remarkable characteristics. According to Preparation and Use of Lime Mortars published by Historic Scotland, Technical Advice Note 1, revised 2003, traditional lime mortars have properties that make them superior to modern cements for the restoration of historic buildings. Lime mortar is more flexible than Portland cement, allowing it to accommodate structural movements without cracking, and it is permeable to water vapor, allowing moisture to evaporate instead of being trapped in. Historical documents such as A Treatise on Calcareous Mortars and Cements by John Smeaton, 1791, describe a process for producing high-quality lime, but details of timing, temperature, and quality judgment were practical knowledge. Smeaton discovered through experimentation that lime made from limestone with clay impurities, hydraulic lime, had superior properties for underwater construction, a discovery that contributed to the later development of Portland cement by Joseph Aston in 1824. Another well-documented material is wrought iron, widely used in construction in the 19th century before being replaced by steel. According to the book, The Making, Shaping, and Treating of Steel, published by the United States Steel Corporation, multiple editions since the 1920s, considered a standard reference in metallurgy, wrought iron has a unique microstructure with silicate slag fibers interwoven throughout a matrix of relatively pure iron. This fibrous structure gives the material excellent fatigue resistance and the ability to deform significantly. Before fracturing, wrought iron was produced through a process called puddling, developed by Henry Cort in 1784. The process involved heating molten iron in a reverberatory furnace while a worker stirred the mass with long tools, oxidizing carbon and impurities. The resulting iron was then repeatedly hammered to consolidate and elongate the slag fibers. The process required skillful judgment regarding temperature, mass consistency, and the exact point of removal from the furnace. As documented in the autobiography of Sir Henry Bessemer, 1905, when Bessemer developed a process for mass-producing steel that eventually replaced wrought iron, it was more economical, but produced material with different properties. Today, true wrought iron is rarely produced, and complete knowledge of puddling has been largely lost. Gothic Revival architecture and intuitive structural calculation. Neo-Gothic cathedrals and churches of the 1800s employed complex structural techniques. According to the book, The Gothic Revival by Kenneth Clark, John Murray, 1928, reprinted by Pelican, 1964, revivalist architects carefully studied medieval cathedrals and attempted to recreate structural principles. Jacques Heyman, professor of engineering at Cambridge, and author of The Stone Skeleton, Structural Engineering of Masonry Architecture, Cambridge University Press, 1995, demonstrated that Gothic structures function primarily through pure compression, and that medieval builders developed sophisticated empirical rules for providing structural elements. These rules, such as the thickness of a wall should be approximately 1/10 of its height, or that a flying buttress should have sufficient mass to counterbalance the horizontal thrust of the vault, were not derived from formal mathematical calculations, but from careful observation of what worked. Architects of the 1800s, such as Augustus Pugin and George Gilbert Scott, studied medieval treatises and measured existing buildings to derive these proportions. A particularly interesting technique documented by multiple historians is the use of hanging chain models. When a chain is hung freely between 2 points, it assumes the form of a catenary, a curve that minimizes gravitational potential energy. If you invert this form, you obtain an ideal arch shape that supports its own weight in pure compression without tension. This technique was famously used by Antoni Gaudí in the early 20th century to design the Sagrada Familia, but the principle was known to earlier builders. Robert Hooke described the concept in the 1670s with the statement, ut pendit continuum flexile, sic stabit contiguum rigidum inversum, as a flexible continuous hangs, so a rigid contiguous hangs inverted. Documentation of the use of physical models by Gothic architects appears in multiple sources, including Gothic Architecture by Paul Frankel, Yale University Press, 1962. The combination of emerging theory, Galileo studied the strength of beams, Euler developed buckling theory, Navier worked on elasticity, with empirical knowledge and physical models, allowed architects of the 1800s to create complex and efficient structures without computers. Victorian precision instruments and dividing machines. Victorian scientific instruments represent the pinnacle of precision craftsmanship. According to A History of the Machine Tool Industry by L.T.C. Rolt, 1965, and the work of technology historian Robert Woodbury, such as History of the Gear Cutting Machine, MIT Press, 1958, the manufacture of precision instruments in the 19th century depended on specialized machines such as dividing machines. A dividing machine was used to engrave graduated circles on instruments like theodolites and sextants. The machine used a precision screw and gear system to rotate the circle in exact increments while the tool engraved divisions. The precision of the final instrument depended on the precision of the screw in the dividing machine. A fundamental problem documented by Woodbury was how to make the first precision screw. The historical answer involved an iterative process called precision regeneration, or self-generated accuracy. The craftsman would start with an approximate screw, use it to make a slightly better screw through careful measurement and error correction, then use that to make an even better one. This process was described by multiple historical instrument makers. Henry Maudslay, 1771-1831, was a crucial pioneer in this process, creating the Lord Chancellor, an exceptionally precise standard reference screw used to calibrate other screws. According to biographies of Maudslay, including Henry Maudslay and the Pioneers of the Machine Age by J.W. Rowe, 1916, he spent years refining screw machining techniques. Joseph Whitworth, 1803-1887, took precision even further, developing methods for measuring with accuracy to a millionth of an inch, approximately 0.025 microns, documented in his own technical writings. Knowledge of how to make these measurements and corrections was partly technical, specific measurement methods, and partly tacit, tool feel, visual judgment. Apprentices spent years working under masters to develop these skills. Today, precision screws are machined on computer-controlled CNC machines, but the historical process of precision bootstrapping through iterative manual refinement represents a remarkable achievement of tacit knowledge. Technical textiles, naval, linen, and traditional sails. The textile industry of the 1800s produced technical materials with remarkable properties. According to Textiles in America, 1650-1870, by Florence Montgomery, W. W. Norton, 1984, fabrics for specific applications such as ship sails were produced to rigorous specification. Sails were traditionally made of linen or hemp, materials that combined strength with durability against the elements. The production of high-quality linen involved multiple specialized steps. Flax plants, Linum usitatissimum, were cultivated in specific regions known for ideal conditions. According to the Linen Trade Ancient and Modern by A.J. Warden, 1864, the Ulster region of Ireland was particularly famous for quality linen. After harvesting, flax stalks underwent a retting process, where they were immersed in water to allow bacterial decomposition of pectins that bind fibers. As described in historical treatises on linen production, retting timing was critical. Insufficient retting left fibers stiff and difficult to process, while excessive retting weakened the fibers. Craftsmen judged the ideal point by inspecting the stems. After straightening, fibers were extracted, cleaned, and spun into yarn. Weaving was done on looms, which, although progressively mechanized during the Industrial Revolution, still required operator skill. Fabric underwent finishing treatments that affected final properties. Complete production knowledge, from plant variety selection to final treatment, was distributed through a chain of specialists. Written documentation captures the general process, but not all the nuances of judgment at each stage. Replacement by synthetic materials in the 20th century meant that much detailed knowledge of natural fiber production was lost or remains only in small artisan communities. Acoustics of 19th century concert halls. Concert halls built in the late 1800s are the subject of extensive study by acousticians. According to the definitive book, Music, Acoustics, and Architecture by Leo Beranek, John Wiley and Sons, 1962, updated in multiple editions, the Musikverein in Vienna, 1870, and the Concertgebouw in Amsterdam, 1888, are among the halls with the best acoustics in the world. Beranek and other acousticians have measured these halls extensively and attempted to identify what makes them special. Factors include volume per seat, reverberation time, ratio of direct to reflected sound, and distribution of first reflections. But even with detailed measurements, replicating acoustics has proven challenging. As documented in Concert Halls and Opera Houses by Leo Beranek, Springer 2004, multiple modern halls have been built attempting to replicate the acoustic characteristics of successful historical halls with varying results. The problem is that acoustics result from a complex interaction between room form, surface materials, ornamentation, and even the presence of an audience. Historic architects did not have modern acoustic equations. Wallace Sabine's fundamental work in architectural acoustics only began in 1895-1900. They relied on empirical knowledge transmitted through building tradition, combined with experimentation. Some used scale models. Some made adjustments during construction based on testing, as noted by acoustician Christopher Jaffe in Orchestra Shells, Journal of the Acoustical Society of America, 1976. Seemingly minor details, such as the specific type of plaster on walls or the configuration of ornamentation, can affect acoustics in counterintuitive ways. When historic rooms are renovated, there is a risk of inadvertently degrading acoustics if renovators do not understand the acoustic function of elements that appear purely decorative. Metallurgy, Damascus steel and crucible steel. Damascus steel, although older than the 19th century, has remained an object of fascination. Modern studies using electron microscopy and other advanced techniques, such as the work of J.D. Verhoeven and colleagues published in Damascus Steel Part 1, Indian Wootz Steel, Metalography, 1987, have revealed a complex microstructure with carbide patterns that contribute to remarkable properties. Knowledge of its production was lost in the 18th century, illustrating how techniques can disappear. For the 19th century, Sheffield crucible steel is a well-documented example. The crucible process involved heating iron and other materials in a sealed ceramic crucible in a high temperature furnace for an extended period. Benjamin Huntsman developed the process in the 1740s in Sheffield, England, and it became the standard for producing high-quality steel used in cutting tools and precision instruments. According to Sheffield Steel by Casey Barraclough, 1984, stated that crucible steel had remarkable uniformity and purity because long periods at high temperatures in a closed crucible allowed for complete carbon diffusion and homogenization. The process required skillful judgment of furnace temperature and timing. Knowledge was maintained within a community of Sheffield masters and transmitted through apprenticeship. When mass steel production processes such as Bessemer, 1856, and later the electric furnace became dominant, crucible steel production declined. Today, it is rarely produced, and some aspects of process control have been. Modern metallurgists can analyze the microstructure of historical steel and replicate it approximately, but not necessarily with exactly the same process. Preservation of tacit knowledge in the digital age and contemporary cases. The challenge of preserving tacit knowledge is recognized by historians of technology and practical organizations alike. UNESCO has included multiple traditional craft techniques on its list of intangible cultural heritage since its creation in 2003, recognizing that technical knowledge embodied in human practice is valuable and at risk. The list includes techniques such as traditional Japanese washi paper production, traditional French carpentry, and Murano glassmaking. The Heritage Crafts Association in the United Kingdom maintains a red list of endangered crafts, updated biennially. The most recent edition documents techniques with few remaining practitioners, including bell rope making, goldsmiths specializing in specific techniques, and traditional windmill builders. In an engineering context, there is growing recognition of the value of hands-on education documented in academic literature. The article, Engineering Education and the Development of Expertise, by B. Williams et al. in the Journal of Engineering Education, argues that hands-on experience is critical to developing an engineer's intuition about the behavior of materials and systems. MIT maintains a well-equipped workshop where students can learn traditional machining on handheld machine tools before progressing to CNC. The program was deliberately maintained because the college recognizes the value of students developing a tactile sense of how metal behaves under cutting tools. Historic building preservation programs maintain expertise in traditional techniques. The National Park Service in the U.S. operates the Preservation Trades Network, which connects artisans specializing in historic building techniques. Historic England, formerly English Heritage, maintains specialists and offers training in techniques such as traditional stonework, thatched roofs, and historic carpentry. When a cathedral or listed building needs restoration, these specialists are consulted to ensure that work is done using appropriate techniques. Specialized schools also preserve knowledge. North Bennett Street School in Boston, founded in 1881, teaches precision crafts including fine joinery, piano making, watchmaking, bookbinding, and violin making. The program is intensive, typically 2 years of full-time training, recognizing that mastering a craft takes significant time. Westdean College in the UK offers similar programs in conservation and traditional crafts. Digital technologies are being explored as documentation and teaching tools. The CraftML, Craft Machine Learning, project at multiple European universities is attempting to use computer vision and machine learning to analyze videos of artisans at work and extract patterns of movement and technique. The idea is not to replace human learning, but to create richer teaching resources. Virtual reality is being experimented with for training in some techniques, allowing practice without risk or waste of expensive materials. But as argued by Harry Collins in Tacit and Explicit Knowledge, University of Chicago Press 2010, there are fundamental limits to what can be externalized. Collins distinguishes between knowledge that is implicit, but can in principle be made explicit with sufficient effort, and knowledge that is genuinely tacit and resists complete externalization because it is fundamentally embedded in the body and social context of practice. Contemporary cases of rediscovering lost techniques illustrate both challenge and possibility. When a Stradivarius or Guarneri violin is analyzed using modern techniques including computed tomography, spectroscopy, and acoustic analysis, we can learn a great deal about the wood used, the thickness of the plates, and the properties of the varnish. But replicating an instrument exactly has proven challenging. Multiple modern luthiers produce violins of exceptional quality, sometimes preferred in blind tests compared to Stradivarius, but through a combination of understanding scientific principles and developing their own tacit knowledge through years of instrument making, not through simply copying historical instrument measurements. A project to reconstruct historic wind-powered water pumps in the Netherlands offers another example. Dutch windmills included specialized variants used for pumping water from polders, critical for water management in a country below sea level. When these windmills were replaced by diesel and electric pumps in the 20th century, knowledge of construction and operation began to disappear. Preservation organizations such as De Hollandsche Molen have extensively documented remaining windmills and trained a new generation of millers, molenaar in Dutch, to operate and maintain historic windmills. This knowledge is partly technical, such as adjusting sails for different wind conditions, and partly tacit, the sound and vibration the windmill makes when functioning correctly, developed through experience. Implications for modern design and engineering. The study of historical techniques offers lessons for contemporary practice, in addition to its value in heritage preservation. The first lesson is about multi-criteria optimization. As argued by Henry Petrosky in To Engineer is Human, St. Martin's Press, 1985, and other works on engineering philosophy, historical solutions often represent optimization within a specific set of constraints, including available materials, available tools, and available skills. When context changes, the optimal solution changes, but this does not mean that the old solution was universally inferior, only optimized for a different context. The second lesson is about resilience through diversity. When an entire industry converges on a single technology, systemic vulnerability is created. If that technology fails unexpectedly or proves inadequate for a specific application, there is no ready alternative. Maintaining a repertoire of different approaches, even if they seem obsolete, provides options. The third is the recognition of the value of tacit knowledge, even in the digital age. Modern engineering culture appropriately values quantification and computational modeling, but there is a risk of underestimating knowledge that cannot be easily captured in equations. Engineers with hands-on experience with materials and processes develop intuition that complements formal analysis. When computer simulations suggest something unexpected, an engineer with practical experience can judge whether the result is likely genuine or a model artifact. Fourth is about learning. Studies of engineering education show that students learn in different ways and that combining formal theory, computer simulation, and practical experience provides a more robust education than either alone. Practical projects where students build physical artifacts, even simple ones, develop problem-solving skills and an understanding of uncertainty and variability that are difficult to acquire through theoretical work alone. Fifth, there are direct applications of historical techniques in modern contexts. Sustainable architecture is rediscovering vernacular building techniques that work with local climate and use minimally processed local materials. Techniques such as rammed earth construction, dry stone walls, and green roofs are thousands of years old, but are relevant to reducing the carbon footprint of buildings. Biomimetic design looks to natural structures and also historical structures that have evolved over generations for insights into efficient material solutions. Finally, there is ethical consideration regarding professional responsibility. When engineers or architects work on the restoration or modification of historical structures, they have a responsibility to understand original techniques and not inadvertently degrade the structure through ill-informed interventions. This requires humility to recognize that historical builders may have known things that are not immediately obvious to the modern practitioner. If this exploration based on real historical research into lost technical knowledge fascinated you, leave a like now. Subscribe to the channel for more investigations based on verifiable sources. Click on the video appearing on the screen to continue exploring the history of technology. Thank you for watching and for valuing content based on genuine research. Links to mentioned sources are in the video description. See you in the next video.